All right. So this is our last day on our unit on ecology. This will be day 4, and what we're going to talk about today are ecological succession and human impacts. So, ecological succession. Basically, what ecological succession means is so we, of course, have an ecosystem, and then succession would be how an ecosystem progresses or grows after some type of disturbance. Some disturbances can be quite harmful and bad to the ecosystem. Um, and so it might have to do a lot more work to get there, and then some just kind of are a minor disturbance. And so there's going to be two types that we're going to look at. So in this, you're going to hear about some terms called a pioneer species. You're also going to hear the term climax community. Pioneer species are what comes first, and a climax community is where it is at its peak. And so we're talking about if it's a full on having to start at the very beginning because there's not even nutrients in the soil. I mean, we're talking about. I mean, I guess it really depends on the type of accident that occurred, but you could still be looking at hundreds of years there to be able to form that climax community again. And of course, it also depends on what type of biome and where you're at in the world. Because if you're in an area that, you know, those mature oaks, so that its climax community can look very different depending upon where you are in the world and what type of biome you're in. Because, grasslands don't support because of the high winds, um, forest fires and things like that. They don't really support the big oaks and things like massive forest in that sense. So it does depend on where you're at, but this is more of a general thing of what we mean by climax community typically and pioneer species. So the first one is a primary succession. Primary succession would be whenever the disturbance to the ecosystem was so severe that it actually causes it to start at bare rock, meaning that the soil is not even it's not nutrient rich, which means that plants can't live there or anything. So what has to happen first is we actually have to start breaking down that rock. We have to weather it down through the wind and the water, and so of course that's going to take a long time. Some of your pioneer species, such as mosses and lichens, sometimes referred to as lichens by some, but lichens, um, start to grow. And as they die, and these are actually kind of unique organisms. They're especially those lichens. It's like they're a plant and they're a decomposing fungus as well. They're just kind of unique in that sense. But basically, as they die and decompose, um, their nutrients starts to add to build to that soil, and it starts to build up, and that actually adds nutrients to it, and then over time, it'll actually build up enough soil to where grasses could grow. And then from there, we could go through that succession process. But in primary succession, it is important to know that, of course, we're talking about having to start with bare rock. Uh, there's no nutrient rich soil. The pioneer species would be like mosses and lichens. Um, And some common examples would be like a retreating glacier, a volcanic eruption, strip mining, and a WMD. If you don't know what a WMD is, that would be a weapon of mass destruction, like nuclear and atomic bombs, things of that nature, that would destroy and kill all of those things. The second type is secondary succession. So most of your questions here are going to deal with knowing the difference between the two, and if I give you an example of what has happened to a general area, being able to decide is it secondary or primary succession. So secondary succession deals with the disturbance to an ecosystem that drives out or kills the surface organisms. Probably one of the best examples I can think of is a forest fire. Forest fire is bad. It's going to kill the grasses. It's going to kill the trees. It's going to drive out all the animal life in that area. But at the end of the day, the soil itself is actually still rich. And after that fire, actually the soil will even become more rich, meaning that the first thing that will start to live there is grasses. Mosses and lichens won't have to build up the nutrient rich soil. So that's one of the most important differences between the two. Primary succession's having to start at bare rock. Secondary succession, there's nutrient rich soil there, and it's ready to start growing new organisms immediately, such as grasses. Some common examples there. I gave you one for forest fires. We could also talk about deforestation. Just because you go through there and you kill a bunch of trees, grasses and weeds and things like that are going to be growing there by the next year. Reclaimed farmland, that's a really common one. Basically, you think about it, whenever if there was a big wooded area and then somebody came through there and cut down all the trees so they could have farmland, that's basically what they did there. They drove out all the surface organisms, and well, what's the first thing that started growing then was plants, was grass. The reclaimed farmland could also be whenever that farm is left unattended. Eventually, the grasses, other tree species will start growing in, shrubs, bushes, things like that. Pine trees will start growing. Some of those evergreens will start growing, those softwoods. And then eventually, those hardwoods would move in. And then next thing you know, you have a big, beautiful forest again. It'll only take, 150 years or so. So here's a good example of a secondary succession. This is about a 5 year difference, I believe it is. Or maybe it's actually no, it's the next. It's the very next year because I see the trees are still burned there. But you notice this was taken after a forest fire, and then by the next year we already have green grass growing in. Okay. So here's kind of one to kind of show you from that pioneer species to that climax community. So over here in secondary succession, we had a forest fire. And then right here along the bottom, you see that we have the years that it's taken to be able to move through it. So each frame of this represents that same beginning frame of where that forest fire was, and then as we move through it. So at year zero, of course, that's what was happening there. But then the next thing you know, we already have grasses moving in by the next year, and 2 years later, we have grasses moving in. We're getting to where now we're going to actually have some grasses and some perennials. That would be the plants that come in every year. And then we're going to start getting, we're still going to, of course, have those intermediate species now. We're still going to have grasses, but now we're going to start getting some of those really young oak trees, but mainly we're going to start seeing a lot of pine trees that are softwoods, shrubs, bushes, things of that nature. And then the very end here, we're going to be having our climax community. If you notice, what this dark line represents is this dark line represents that beginning of where it was, and then all this stuff that's above that dark line that's running through it, that would be the soil buildup from that initial disturbance. And then by the end of it, we have that climax community. And again, this could easily take 100, 150 years without any problem of just a forest being left to itself to have to repair after a damage. We also see that with an aquatic succession. I've seen this on some family land. Places I used to go fishing at as a kid are almost completely filled in now, and that's due to sediments filling in. And now, of course, out there, we're talking about a big forest where I was at. But basically, what starts to happen here is sediments start to build in the water. And as it builds in, it actually cuts off the amount of water that's available to other organisms, and other plant life's able just to grow in it much easier. And then eventually, over time, it'll completely fill in there. So this would be, another example of how density dependent versus independent factors, and how organisms, are interacting constantly with their environment. And this term right here is turbidity. That means whenever I say dirty water, I'm talking about the amount of sediments that are in the water that cause it to not be very clear, such as because we have so many mud bottoms and dirt bottom rivers and lakes and streams in Mississippi, we can't really see through ours. But if you go to areas of the world or in areas of the United States that have rock bottom streams and rivers, you can see straight through it and see the fish and all that kind of thing. So their water wouldn't be very turbid. So talking about deforestation, of course, deforestation is whenever you're having the mass cut down of trees and the problems that it causes. So of course, deforestation causes problems dealing with the burning of the timber because that's going to increase carbon dioxide, which is a greenhouse gas. We're going to talk about that in just a second. Less trees means less carbon dioxide is absorbed. So again, you cut them down, you burn them, so there's more carbon dioxide. But because you cut them down, there's less trees to absorb that carbon dioxide, which again increases greenhouse gases in our atmosphere. It also increases soil erosion because the roots of plants and trees, they actually hold soil in its place, which actually increases turbidity in water. Um, and then, of course, habitats are destroyed as well. We also have a term known as bioaccumulation. This is basically whenever toxins are emptied out into a waterway, they find themselves into a waterway is one of the most common examples. And because of that, they find themselves in the food web or the food chain of that ecosystem. But bioaccumulation refers to these toxins. They're not like other things that actually reduce as it moves up. It actually increases. So as the zooplankton eats the phytoplankton, the amount of toxins that are inside the zooplankton actually increased. So if you notice, it went from 0.04, and right here it says parts per million, to now it's at zero point 0.2 parts per million. But then as the small fish eat the zooplankton, that went up again to 2 parts per million. And then as the osprey and the bald eagle eat those fish, it went up yet again. And so that's how that toxin is accumulating in that ecosystem. Common places where you find DDT, pesticides, herbicides. So if a farmer is spraying these type of toxins on its plants, on its crops, and then it rains, and then that of course goes into the runoff, gets into rivers, lakes, and streams, and that's how it enters this food chain. Now we're going to go to greenhouse gases. So a greenhouse gas, like I said earlier, they're not bad. We actually need them. They're going to insulate our planet, and without them, we'd be a frozen world and nothing would live. The problem is the amount in which we are accumulating those greenhouse gases. The overproduction of greenhouse gas, though, actually causes the Earth's temperatures to increase too much, harming life on Earth. Now, one thing that's misleading here that a lot of people that I see a lot out there in the news or even hear people talk about is they make this assumption that we mean that it's going to be increasing at such a dramatic rate that last summer our average temperature was, let's pretend, 90 degrees, and this summer it's going to be 120 degrees. That's not that's an oversimplification, and that's actually taking this information way out of proportion. This is going to be a very slight change, but we will start to see an increase in it, and we've actually already have measurable data to show that increase. Common greenhouse gases would be carbon dioxide, methane, even water vapor. Excessive amounts of water vapor are greenhouse gases that can trap heat in the atmosphere. So anything that can trap heat is a greenhouse gas. The problem is that we're actually directly causing an overproduction of carbon dioxide and methane. Um, and that's of course due to human activity, especially over the past 150 years, industrial revolution, factories, automobiles, things like that, burning coal, burning oil, all that type of stuff in a massive amount beyond which nature naturally has. Because I mean, nature puts it up there through volcanoes, natural forest fires due to lightning strikes, wildfires like that, or just organisms that breathe out carbon dioxide puts carbon dioxide in the air. But one thing that organisms don't do is mass deforestation and burning of fossil fuels at a unprecedented rate in the past 150 years. So what these greenhouse gases do is really the best way to think about a greenhouse gas is like it's a blanket, and this blanket surrounds our atmosphere, and it actually holds in heat. And so imagine if you're asleep in bed, you want to have one blanket on you and you're nice and you're comfortable with it and it's not a problem. But if somebody adds another blanket and then another blanket and then they keep adding blankets to you, what actually is happening there is the heat that your body's producing is actually getting trapped in due to all that insulation from that blanket, and it's actually going to cause you to overheat and start to sweat. Well, you have the ability to just throw the blankets off if you no problem. The problem is that the Earth really doesn't have that ability just to do that all of a sudden. There actually has to be actions to take place on our behalf, such as we have to stop, cutting down so many trees. That way, the plants can do what they're supposed to do, take in that carbon dioxide. Also, we have to produce less of it. That way, we're not adding blankets on top of us constantly. What the greenhouse effect will actually cause, will actually have disturbances in weather patterns. It can even increase droughts in areas, floods in other areas that normally wouldn't have floods, hurricanes and typhoons. It doesn't mean that, oh, you know, if we have global warming means that you won't be cold. We're really talking about a disturbance in weather patterns, and so an overall temperature of the Earth though could or is increasing. So what we have here are some figures put out. I found this the image through NOAA, NOAA, and basically this is data that they found and through which they measured. So they were looking at the amount of carbon dioxide, and this is going back to 1978 to 2010. And you can even find more recent figures in this. I just like the fact that this image had the main things that we're talking about all on one image itself and not on a lot of different ones. So if we notice, just since 1978, we see that the parts per million on carbon dioxide has gone from just a little less than 340 to over, and actually, and probably now it's definitely over 390. I would assume based on this graph, I could extrapolate that by another 10 years and say, heck, it could probably end up being over 400 million parts per million. Same thing with this nitrous oxide. But if we look down here at this methane, the methane here, this says parts per billion. So we are really increasing the amount of methane production. And then, of course, we have this CFC. The CFC stands for chlorofluorocarbons. And really what we see here is, I remember whenever I was growing up around the 90s, mid 90s, even going into the late 90s, there was this big thing about hairspray and aerosol cans, about how they, whenever you spray them, they're actually bad for the ozone layer because they break down the ozone layer. Well, that's because those chlorofluorocarbons break down the ozone, and ozone is a molecule. And then you started seeing restrictions on that, and that's whenever you see this leveling off here, where it's not really increasing as much anymore, and it might even be going down if we had more recent information. So that's that. And you'll even see graphs similar to this that'll kind of ask you what it means. And so that's important to be able to look at that data. Right here, we can look at global temperatures since we've been taking global temperatures from different meteorological stations around the world. And if you notice, that red line would be kind of like its mean over that 5 year period there, and we see that what has happened is, yes, we have some years where it's more warm and other years where it's cooler. But what we start to see here is we actually are starting to see that we're almost at a at 1 degree higher since, let's say, at for the past, probably, was that 80 to 100 years, we're about a degree higher since then. And we've seen a massive uptake since the 70s, or since the, probably, late 60s. We've seen a massive uptake in the amount of, in our temperature there. We've seen a lot more dramatic rise there. Here's another image. This one right here was actually taken from ice cores from the, I don't know if it's from the North Pole. I'm assuming North Pole is where they typically do that. But what they're doing is actually they're measuring the amount of carbon dioxide level and they're able to use that to determine temperature and things like that of an area by looking at the amount of carbon dioxide that was in the that was inside the core of the ice samples that they're taking out of the North Pole. But what you see over the past 1,000 years is the amount of carbon dioxide has stayed pretty stable, and with that, the temperature ranges has also stayed pretty stable as well. A little bit of up and down, but still everything's relatively stable. But once we start hitting the globalization and we start having the Industrial Revolution toward the late 1800s, early 1900s, and that means that with that Industrial Revolution, we have a massive amounts of burning of fossil fuels and oil, carbon, coal, all that type of stuff. We see a massive increase in the amount of carbon dioxide, and with that, the temperature increase as well. That's the data that people bring forward whenever they talk about it. And remember, this isn't a dramatic. Whenever we say dramatic increase in temperature, you have to remember that if I increase your own body's temperature by a degree, you actually start to feel bad. You can make it, you can tough it out, but you actually do start to feel differently. But if I increase your body's temperature by another degree, you really do start to feel bad. After I increase your body's temperature by 3 degrees, you really, you're really sick, and and are very ill. Same kind of thing can happen with our planet. As we increase its temperature, it will start to show more and more symptoms, and the symptoms will be even more harsh than the ones before. And so that's the reason why there's this push on trying to have more environmental conscientious talks of being more environmental conscientious. All right. So that is all of our information from this unit. I know that was a lot, but we do have those practice questions, and we'll have more discussions on this in class. Thanks.